Good afternoon, everybody. My name is Rez Mani. I work for a company Allied Scientific Pro, and welcome to our laser cleaning webinar today. My email is mentioned at the bottom of this PowerPoint, and it will be sent to you as an attachment. The whole PowerPoint with the recording will be sent to you as an attachment or a link at the end of the webinar. So if you have any questions, feel free to ask me, send me an email and ask me. Or if you need to stop me in the middle of the presentation, that's fine too. So you can stop and ask questions. Or if you like, you could wait till the end and we have a question Q&A period. We can talk after. So today's webinar is about laser cleaning principles, the basics basically, and some examples that I'll show of this laser cleaning. So the topics that I will be covering during this webinar are the following. First, I'll give an introduction to laser ablation. What is the process of laser ablation? And then we will talk about laser in general, the laser medium. Some lasers have gaseous medium, some have crystal, some have fiber optic. So just some basic information about laser. Then we will talk about the types of lasers that are used in laser ablation. And again, some of these could be crystal based, and some of them are fiber based, and some of them are gaseous based. Then we will see how we use laser ablation for laser cleaning. So for laser cleaning, certain parameters are needed. So we have to choose those parameters carefully to be able to clean a thin layer, for example, on top of a bulk of a substance. Then we would compare this with other competing surface cleaning techniques. There are mechanical techniques, and there are other chemical techniques, mechanical techniques of cleaning. So we would compare laser cleaning with those. Then we would get into a little bit of physics of what's going on and the dependence of laser ablation on material properties and laser parameters. And then there are different types of lasers as far as pulse widths are concerned. There's a femto-second, 10 to the minus 15 pulse width, pico-second, 10 to the minus 12, and nanosecond, 10 to the minus 9. And each one is useful for a different application. And I will give some examples of laser ablations along with videos. And these examples are cleaning of artwork and historical monuments, removing paint from aircraft, nuclear decontamination. And at the end, I'll show some videos of laser cleaning systems that Allied Scientific Pro offers, followed by some conclusions. Next, so principle of laser ablation. Laser ablation is the process through which a high-power laser is focused on a surface and removes material from it. So basically, you're focusing an intense laser beam, which are normally pulsed on a surface, and that evaporates material from the surface. This laser ablation could be not only for laser cleaning, but it could be used for laser machining, laser cutting, paint removal, contaminant removal, drilling, scribing. But our focus in this talk would be laser cleaning. But all of these techniques use laser ablation. Although both CW pulse lasers are used for laser ablation, the usage of pulse lasers is more common. And for the reason that there are parameters that you can play with. You could play with the pulse width, with the pulse repetition frequency, and things like that. Whereas in CW laser, you're pretty much confined to the intensity of light that you're getting. So I think the control in case of pulse lasers is more as compared to CW lasers. So now I want to show you a laser ablation video. This is some kind of animation of how laser ablation takes place. So let's look at this video and see how. So this is a cube, and then the laser beam is focused on the surface, and these are the ablated materials that are ejecting out. Basically, if the laser beam is not too strong, it just evaporate the material. But if it is too strong, then it would make a plasma. So basically, the gases that are produced are ionized and makes a plasma. So this is like some kind of animation that shows what laser ablation is. Okay, so next, let's go back to the presentation. Right. Next, so principles of laser ablation. Let's talk more about this. When the laser beam irradiates the surface, it either evaporates the surface at lower energies above a certain threshold level or will form a plasma. Sorry, I'm just gonna have to mute this. Sorry about that. So it will either evaporate at lower energies or will form a plasma at higher energies. And this formation of plasma at higher energies actually is pretty useful if you want to know the chemical composition of the material. And there's this technique called LIBS, L-I-B-S, which stands for laser-induced breakdown spectroscopy. And when the laser flux is high and this plasma is produced, you could look at the light that is generated by this plasma and then take it to a spectrometer and see what is the chemical composition of the material, and that is preferred method to using strong acids, which require sample preparation and may destroy the sample. Now, the process of laser ablation would have one particular application, and that is to remove thin coatings from material surfaces such as rust, paint, oxide, or for example, to remove paint from a surface, and this is called laser cleaning. The depth over which the surface is ablated depends on its material properties and also on the laser properties such as wavelength, pulse energy, and pulse length. And we'll talk in more detail about these parameters, which are very important to be selected. If you use incorrect values for the laser parameters, you may damage the surface. You may damage the bulk of the surface. Say if you're trying to remove paint from an aircraft and you're choosing incorrect laser or incorrect parameters, you may actually damage the body of the aircraft, the metal body of the aircraft. So you don't want that to happen. So for this reason, you need to choose the correct laser parameters. Now, total amount of material ablated from the surface per pulse is called ablation rate. This is a definition, and this also depends on laser beam scanning velocity. So the faster the beam moves, the higher is the ablation rate. Next, important parameters for laser ablation. Yes. So what are the important parameters for laser ablation? They are wavelength is number one. Some wavelengths are heavily absorbed by some materials and others are reflected. It depends on different materials as well. For example, metals heavily absorb near IR but reflect most of the far IR. But polymers absorb mid IR better than near IR. So depending on what material you're using, what is the substrate, which you are careful not to damage, you have to choose the right wavelength. So CO2 lasers, for example, have mid-IR wavelength, so they are probably suitable to remove paint from a metal surface because the metal reflects the mid-IR wavelength or mid-IR radiation. But the paint heavily absorbs it. So the danger of damaging the metal substrate is minimal if you use a mid-IR laser for paint removal. But and then there are other applications. The other parameter is pulse width. The depth of ablation may depend on pulse width. Thermal penetration depths will be introduced later. This is something I will talk about later. So longer pulse width will have more penetration depth and require higher energy per unit area to ablate the material. So normally when you have a short pulse width in the femtosecond region, the thermal effects are less, but if you have nanosecond pulses, the thermal effects are more, and that's a parameter to be considered. So we will talk about that later when we get to the physics of the whole thing. Then the pulse energy, of course, when there's more pulse energy, there's more ablation because more material will be heated and removed. So that is also showing in the form of something called fluence, which is pulse energy per unit area. And that's also another parameter that we'll talk about later. Beam shape for different applications for laser ablation, you have different shapes. If you want to micro machine something, you need to basically use a very narrow and small beam. But if you want to remove paint from a surface, you could usually use a line, maybe about 3 or 4 centimeters or even 10 centimeters long, maybe 2-3 millimeter wide, because this way the efficiency of paint removal will be more. So beam shape is another factor. And then rep rate, finally, increases the depth of ablation. So higher rep rates will remove more of material. So these are some important parameters that we talk about. Now let's talk about laser medium. Just a brief introduction to lasers, just in case you know, someone may not be familiar with the basic principles of lasers. It's also useful to look at how these laser beams are produced. So I've just made this YouTube video. I found this YouTube video which shows it really well. So let's watch this together. So I'm just muting it, explaining it to you. So you can see an atom here. There's the nucleus of atom, and these are the electrons that are going around there. And this atom could get excited. If it absorbs the photon, it could, the electron could go from a lower energy level to a higher energy level. And when it basically comes down from that higher energy to a lower energy level, it releases an identical photon. And this is called the stimulated emission. So here you can see if you have 2 mirrors on either side, you know, these photons, that they are going through these excited atoms and generating stimulated emissions. And these are all identical photons with the same wavelength and same frequency. And if one of the mirrors is a partially reflecting mirror, all these identical coherent photons will emerge, and that forms the laser beam. So this is how a laser works. So going back to this, in order to excite the atoms, because in order to get the stimulated emissions, the atoms should be excited, you need to pump these atoms. So this pumping of the laser medium could be done either optically, maybe you can shine some other laser onto it, or an arc lamp or something like that to optically excite them, or it could be done electronically. So you could pass a discharge, you could pass an electronic current through the laser medium, say if it is a gas, and excite the atoms. Lasers normally contain a fully reflecting and a partially reflecting mirror, and the partially reflecting mirror is where the laser beam comes out. So this was some introduction about lasers. Now let's get more professional here and look at different types of lasers that are used for laser ablation and also for cleaning. So I've shown 4 different types of lasers here, and there's a table at the bottom which explains the parameters of these lasers, the types, and and the parameters, some typical parameters. It doesn't mean that they should always have exactly the same number, but some typical. So starting from the left, let's look at excimer lasers. There are pretty expensive UV lasers. They're wavelengths ranging anywhere from 126 to 351 nanometers, and basically you can find different types of excimer laser: argon fluoride, xenon bromide, xenon fluoride. These are the wavelengths that are given. They all involve noble gases combined with a halogen, and this could be achieved, this bond could be achieved at an excited state, because normally the noble gases don't react, but at an excited state they could form a temporary bond with the halogen. And then when they get excited, they emit this ultraviolet light. Normally their pulse is nanosecond width, and their applications are in places like photolithography, where it's a process used for microfabrication to pattern parts of a thin film or the bulk of a substrate. Now, what is important about these lasers is that their thermal effects is minimal, and what they do is what they call photoablation is what they achieve, and this would dissociate molecules. Instead of thermally evaporate, it dissociates molecules and it removes them from the surface. So for applications where you don't want heat to damage a bulk of a material, it is very good to use excimer lasers. But they are quite expensive. Now, moving on to the next laser on the left side is a CO2 laser. It's a gaseous laser. And by the way, excimer lasers are gaseous as well. So CO2 laser is another gaseous laser, but this spectrum, the emission is at another part of the spectrum. It's at around 10 micron, which is classified as mid-infrared laser. And so to be exact, it's about 10,600 nanometer or 10.6 micron. It's a gaseous laser, and pulse width about 100 nanosecond, and the method of pumping is just passing basically high energy electrons through it. So this is how you excite it. For the excimer laser, you could either excite it optically through an arc lamp or with high energy electrons. You need cooling for it. And this CO2 laser is quite useful because it's heavily absorbed by polymers and plastics, but not absorbed that well by metals. It's 90% reflective. But there are disadvantages to using this laser because the fiber optic is not available as much as it is in near infrared for the far infrared, and they're also expensive. Next, we go on to neodymium YAG laser. It's a crystal laser, the crystal of neodymium YAG. It has a near IR wavelength, a nanosecond pulse, typically about 10 nanosecond, and you can the pumping method could be a laser diode emission, so optical emission from a laser diode, or an arc lamp could pump these lasers. They're very popular and have many applications, ranging from LiDARs, LiDAR systems for making maps of the terrain, and also for cleaning. And the availability of fiber optics is very important because they can propagate through fiber optics. You can also get the harmonics by putting harmonic crystals. You could double the frequency and get a 532 green beam or a 266 nanometer ultraviolet beam, and they're very useful for laser cleaning as well. And then at the far right, you have the Ti Sapphire laser. Again, it's a crystal laser. It uses the crystal of Ti Sapphire, and it's a femto-second laser, so very short pulses. And it's tunable in the range 650 to 1100 nanometers. So by changing the alignment, you can get different wavelengths. And these lasers are usually used for Semiconductor research, for example, is one area that uses them when you want to explore the band gaps of semiconductors. Or you can also use them for laser cleaning or laser machining, where you need precise cuts. And in some applications, you may be able to use it for cleaning as well. So these are some popular lasers. And then there's other type of laser, which is called the fiber laser. So in all the other lasers that I showed you, there are mirrors. There's one fully reflecting mirror, and then there's a partially reflecting mirror on the other side. But there is possibility that you dope a fiber, an optical fiber, with materials such as ytterbium, erbium, and thulium, which is all rare. All of them are rare earth elements, and then you can make these Bragg gratings. So you can just see in this picture over here, like some lines have been produced in the core of the fiber, and they reflect only a certain wavelength. You can design them so that they reflect a certain wavelength. So basically, it acts as a mirror. So bouncing back and forth between the two Bragg reflectors, you can create a very intense laser beam. So they usually work in the near infrared regime. The pump light is diode laser. They have great flexibility to reach hard to reach places. They're more economical than CO2 lasers, and other advantages include high pulse energy, high average power, good beam quality, and a variable pulse length. And this is an example of a fiber laser. You can also get femto-second fiber lasers that can be used for removal of contamination from composite materials. You have to be careful not to damage the fibers inside the composite materials. So for this reason, you have to use either UV laser, or if not available, you could use a femto-second fiber laser. This way, you would only remove the contaminant layer and not the basically, you won't damage the bulk or the fibers, the reinforcing fibers within the body of the material. So what is laser cleaning? We've been talking about laser ablation mostly, but what is laser cleaning is use of high power pulse lasers to remove material from a surface. Helps to clean the surface. Okay, so these surfaces sometimes could collect rust and layers of sulfate and nitrate for, say, historical monuments, or maybe the paint on an airplane gets needs to be redone because it's coming off. So you need to repaint that. We use laser ablation as a way to clean the surface. It's called laser cleaning. The photothermal effects for near IR and photochemical effects for UV lasers are responsible for this cleaning. Sometimes fiber optics is used to direct a high power laser beam towards a surface that needs to be cleaned. So this picture you see over here is one of the systems that the company Allied Scientific Pro that I work for has produced, and there's a fiber optic. You can see this is the whole laser machine, and this is a fiber optic cable inside there, and then it has the laser head here, or scanner head, has some galvos and some lenses that shines a linear beam towards the target. And let's look at the video of this, how it works. This is a video. It shows how rust is being removed from a pipe. So you can see that the laser is invisible and it's creating this line, and it's removing the rust from this pipe. And this pipe that you see over here is basically a suction pump that removes all the ejected particles. So it will just be environmentally friendly and cleans as it removes the rust. Okay, so moving on, let's move on. Fiber lasers for industrial applications are becoming very popular. This table shows the industrial laser revenues in millions of dollars. And you can see from 2013, 2014 to 2015, there has been a decrease in the usage of carbon in the income or revenues from carbon dioxide and solid state lasers. For example, the neodymium YAG laser is a solid state laser, and the fiber laser has picked up by 13%. So this has been taken from the Industrial Laser Solutions for Manufacturing special report published in 2015. So fiber lasers, due to their flexibility and ease of operation and high power and adjustable pulse length, pulse width, they're becoming more popular and they're used more and more in different applications. So let us now compare the laser cleaning method with some of the other competing methods. So there are other methods of cleaning, and some of them are listed here. Mechanical abrasives, where you actually take a rotating disc and scrub the surface with it. This is one way of doing things. Then there's the chemical method shown here, where you actually apply a chemical to the surface and then wait for a few minutes for some chemical interactions to take place, and then scratch the surface as shown in here. And then you have these dry ice and sandblasting methods that you basically send a high velocity dry ice or sand through a nozzle and clean the surface. Usually these methods, they produce a lot of pollution, a lot of environmental pollution, because they use water sometimes, and the water mixed with the dirt that is coming off from the surfaces have to be taken care of. It's an environmental hazard. So what are the other disadvantages? Create a lot of pollution, debris, which is hard to be cleaned, not healthy for environment, could damage. The other problem, damaging the metal surface, the metal substrate underneath, the scratching and abrasion, and also the impact with the dry ice or sand could damage the underlying surface. Process usually needs an operator, cannot be automated, and it is pretty noisy, 110 to 120 decibel, which is as loud as a siren. Laser cleaning acoustic noise level is about 76 dB, which is the same sound level as a crowded restaurant. So compared to laser cleaning, dry ice and sandblasting are much more noisy. Now, what are the other advantages of laser cleaning? First, it's non-contact. So the only thing that is hitting the surface is light. So there's no solid material that is hitting the surface. Low environmental impact. There's no chemical waste. There's no dirt. There's no contaminated water to deal with. Selectivity, there are certain parameters such as pulse width, wavelength, rep rate that can be tuned to suit some materials better. So this basically control over the parameters are more versatile for laser cleaning as compared to other methods. Localization action only acts where the beam is pointed, whereas if you use a chemical, it could spread over the surface. Versatility, we talked about preservation of surface detail. If you use the correct wavelength, you can, and correct pulse width, you could preserve all the fine details of the surface. And control removal, only a certain control thickness can be removed depending on the parameters that are chosen. Now, I want to show you some videos of other competing techniques. and then you can see for yourself the difference. The only thing I want to point out is that for laser cleaning, there's always a suction pump right nearby where the laser head is that basically takes in all the blasted material and cleans as it's, and basically removes the pollution as it's cleaning the surface. So first thing we're going to look at would be sandblasting methods. Let's look at the sandblasting. So here is a gentleman who's removing paint using sandblasting from a boat. And you can see that it is quite environmentally unfriendly. Next one that we will look at would be water jet blasting is another one. This is water jet blasting. So all this water, contaminated water, is spreading into the environment and has to be dealt with. This is a water jetting method. And then finally, we're going to go to the laser cleaning. Let's look at the laser cleaning. Again, removal of paint from a boat. And you can see this thick tube here basically is the suction pump that takes away all the ejected materials and cleans. Okay, moving on. So let's now go a little bit into the physics of what is going on, dependence of laser ablation on material properties and laser parameters. Deals with the physics of laser ablation and laser cleaning. So what are the important material properties? Is the optical attenuation coefficient, alpha. So how deep does the beam penetrates into the surface? That is determined by the optical attenuation coefficient, and there is this parameter L alpha, which is the optical penetration depth, which is 1 over alpha. And then thermal diffusivity, dt, which is measured in units of millimeters square or meters square per second, and that is basically thermal conductivity divided by density and a specific heat. So that's another parameter. Then of course dt depends on density, and then there's the heat of vaporizations in joules per gram, is how much heat you have to provide to a unit weight of a substance to be able to vaporize it. That's HV. As far as the laser parameters are concerned, type of laser, wavelength of the laser is important, pulse width TL, fluence, which is the pulse energy per unit area. It's a very common term in laser physics, fluence. And the beam size, depending on the application, what size you want to use. So when you have short pulses like femto-second laser, as shown by this orange beam, this orange rectangle shows the beam, you only get penetration depths, which is defined by 1 over alpha. And this is where the energy is confined, only within the penetration depths, not any more than that. There are not much thermal effects involved when you're using short pulse lasers. But when you have longer pulses, then the thermal effects would penetrate into deeper depth, which is represented here by LT. And LT is given by root of dt tau L. But dt is the thermal diffusivity that I talked about, and tau L is the pulse width. So you can see there is a dependence on pulse width. The longer the pulse width, the more is the thermal effects. So a CO2 laser, which has 100 nanosecond pulse width, has more thermal effects than a neodymium YAG that has 10 nanosecond. So for picosecond and nanosecond pulses, thermal penetration depth is greater than optical penetration depth and grows with pulse duration, right? So nanosecond lasers, the thermal and optical are the same. They're not different, but for picosecond and nanosecond, the optical penetration depth could be smaller than the thermal penetration depth. So to achieve ablation, enough energy has to be deposited per unit volume to evaporate the material. The fluence is called threshold fluence. So threshold fluence is the minimum amount of energy per unit area you have to supply to ablate the material. For short pulses, less than 10 picosecond, the threshold fluence does not depend on pulse width and is given by this equation, rho HV over alpha. HV heat of vaporization, rho density, and alpha attenuation coefficient. However, for pulses greater than 10 picosecond, the threshold fluence grows with the pulse width. And affected volume is determined by the size of the thermal penetration depth. So in this case, there is a dependence on the pulse width. And this is a thing to be considered. So here a comparison between the effect of short pulses and long pulses. So femtosecond pulses such as Ti Sapphire laser, suitable for laser machining, or where you basically don't want to have a big thermal effects. You're very careful not to damage the surface, like when it has composite material with fibers, you don't want to damage the fibers. And you can see that this beam it makes a very nice and clear cut. There's no damage to the adjacent structures. There's no plasma plume, no melt zone, no heat transfer to surrounding material, no surface debris. But when you use a longer pulse, nanosecond pulse, or maybe hundreds of picosecond, then you create a shock wave, you damage adjacent structures, you eject molten material, you create surface debris. So much more is to be damaged when you use longer pulses. But in some cases, it doesn't really matter. Even if you damage a little bit of the substrate, it's not that critical. So you can use longer pulses which have higher energies to remove the material faster. But if you're super careful not to damage the surface, then you should use femtosecond laser in short pulses. Here is an example of the effect of long and short pulses. You can see this hole, the same diameter is cut by a femtosecond, very clear cut, no debris, 80 picosecond, an order of magnitude bigger, has some debris, a nanosecond creates a lot of debris around the hole. So this is the difference between the three lasers. Now let's look at some graphs here that shows the behavior of absorption versus wavelength. And for example, you can see here. Let's look at the aluminum here. You can see that at 1 micron, around 1 micron, which is the neodymium YAG laser, it has significant absorption, aluminum. But if you go to a higher wavelength at 10 micron, this absorption goes down. So that's telling us that using a near IR for aluminum may damage the underlying surface, so the substrate. So one has to be careful. But there's still usefulness in using near IR because you can control the parameters properly, and you can also use fiber optics. Here, for example, you can see this case you could use Galvo's fiber optics for some similar laser to neodymium YAG to cut patterns in the soda lime glass, and here is the use of CO2 laser for microstructuring. So mid-IR does not work with fiber optics so well. So but the absorption is the most important thing when you're selecting the proper laser for cleaning. Here's another diagram. It shows that, and a reference is given. These are the UV lasers, 193 nanometer to 48 nanometers, shown in this region. They're excimer lasers. And you can see for plastic, ceramic and plastic, the CO2 lasers work very well. They have high absorption. What the neodymium YAG laser at 1 micron does not have that much of an absorption. So if you're only dealing with removing plastic, it's better to use near mid IR. So for excimer lasers, the absence of thermal effects and basically removal of material by photoablation or dissociation of molecules is a big advantage. Next, application of laser cleaning. Here we have, for example, for neodymium YAG laser, oxides, rust particles, oil-based organics, excimer lasers, UV lasers, oxide, oil and grease, dust, wax, CO2 laser, oxides. So cleaning of historical monuments, cleaning oxide coatings in semiconductor industry, paint removal in aviation industry, removal of rust from pipes, varnished wood, sandstone, decorative steel, decontamination of nuclear power plant. These are some of the applications, and we'll talk about some of them. I'll show some of the videos, some videos for each application. So here, for example, you see laser cleaning of historical monuments. Historical monuments, over the years, they collect layers of sulfate and nitrate, and they need to be cleaned. So neodymium YAG laser is a very good way of cleaning historical monuments, or fiber lasers. Basically, you just want to remove the nitrate and sulfate. And here you can see this obelisk of Pharaoh in Egypt that has been cleaned. And here is stone cleaning of limestone has been cleaned also. Is a piece of art. And you can also clean marble. You can see the statue where half the face has been cleaned. The other half still has all the pollution deposited on it. So I have to mention here that in this case the photothermal effects are not that critical, because you know, you're not dealing with a body of aluminum underneath. So even if you know, there's a bit of photothermal effect, you can still use a neodymium YAG or a fiber laser to clean the historical structure. Now, what are the advantages of this? Is non-contact method. It cleans layers of nitrate and sulfurs. It cannot do anything about acid erosion, because the acids basically cut deep into the structure and eat up the material. So once it's been attacked by acid, nothing can be done. Sorry. No secondary pollution in the form of contaminated water or debris that has to be cleaned, and it's low noise. This statue here is the one that has been attacked by acid, so there's not much you could do about this one. But here is laser cleaning of historical monument shown here, and the laser beam is shown on this side. Next is laser cleaning of aircraft parts. So this aircraft is in a hangar, and the robotics are cleaning it at different angles, so you don't have to rotate the aircraft, and the whole procedure could be automated. So what are the important parameters in this case? Aircraft cannot be repainted, first of all, because it adds to the weight of the aircraft. Old paint has to be removed first. So this is the answer to the question. If somebody asks, why do we need to remove the paint? Why can't we put paint on top of already existing old paint? Because it will add weight to the aircraft, and that's not desirable. So you have to remove it. Then CO2 laser is more suitable because, unlike neodymium YAG, it is not absorbed by the metal underneath. 90% reflected. Then the laser technique, more environmentally friendly than sandblasting, water jetting, and dry ice blasting due to lack of secondary waste and lower noise. And then laser cleaning is fast. So the fact that we said CO2 laser is preferable here was just based on the fact that the metal reflects the mid-IR and absorbs, the paint absorbs mid-IR very well. But you can also achieve the same thing by using near IR if you have very controlled laser beam parameters. So this way you could use the additional benefits of fiber optics and basically the lower costs of the fiber lasers and neodymium YAG lasers as compared to CO2. Next application is in cleaning of nuclear decontamination. So nuclear power plants every 30 to 40 years have to be decommissioned because they collect their parts basically wear out after 30 to 40 years, and their concrete walls, as shown here, they all get, you can say, radioactive material deposited on them, and you cannot just throw them out. You have to first remove the contamination and then throw them out. There is usually cobalt-60 deposit on these, which has a half-life of 7 years, and there are also stainless steel pipes that have been coated by this cobalt-60, so they can be reused and recycled if you remove the contamination. So other methods such as mechanical scabbling and water jetting produce a lot of waste. Laser for ablation have 10 to 100 kilowatt power. Fiber optic delivery is an advantage they could use. And then the downside is that need for laser beam to be focused on the surface, so you need some additional optics. So for another one advantage, on the other hand, is all the material that are ejected are captured by a suction pump in laser cleaning. And this way, one can use laser cleaning as an effective method to clean the nuclear power plant for decommissioning purposes. Okay, so now we just want to show some videos of laser cleaning, and these laser cleaning systems are all made by Allied Scientific Pro. And here in the picture you can see there's this pipe that is just a suction pump that will remove all the debris as it's cleaned. So let's look at some of these videos. This system is called Laser Art, and it's cleaning sandstone from a layer of contamination. This is the pipe that removes the debris. The beam is in near IR, and it's forming, the optics is forming a line. You can also form other types of beam shape, like square or ellipse, depending on the application. Here, this one we saw already. Let's look at cleaning of historical monuments. So this work is more delicate because there are so many features to the historical monument, and the operator is holding the scanner head in his hand. You can adjust the shape of the beam as well. all these videos are available on the website. You can take a look at them if you like. And here's finally laser cleaning of sandstone. You can see the line that has a white color is basically plasma. So the IR beam itself is not visible, but when it hits the surface in glass material, the plasma is generated, and that shows us that white line that you're seeing there. Okay, so let's move on. So let's get to the conclusions. So what are the conclusions? Laser cleaning through the process of laser ablation is more efficient, faster, less noisy, more economical as compared to other paint removal methods such as sandblasting, dry icing, and chemical stripping. And we saw some videos that actually showed that it creates less pollution, it's faster, it's less noisy, it's more efficient. Use of near IR laser with fiber optics makes the paint stripping or contaminant removal very flexible to clean hard to reach places. Industrial fiber lasers are rapidly growing in manufacturing, drilling, scribing, high-speed cutting, paint removal, etc. Laser pulse width, fluence, rep rate, and wavelengths are the important parameters that need to be considered for different applications. Material surface properties need to be considered as well. And we went through the important parameters in the physics part of this presentation. So one has to be very careful about choosing the proper laser and the laser parameters. And basically, if you don't want to create much heat effect, better either use UV laser or use very short pulse wavelength laser. Laser cleaning has several applications in cleaning historical monuments, removal of paint, microfabrication, photolithography, and then the last one, although CO2 laser wavelength is better absorbed by polymers such as paint and reflected by metals, for paint stripping of metal surfaces, NIR laser can be used as well due to their usage of fiber optics and ability to adjust the laser power to below the damage threshold of metal. So you can adjust the laser power very carefully. So although it's being absorbed by the metal underneath, you can still be below the damage threshold. So this way you get all the good things about the near IR laser without damaging the substrate. So that is the end of my presentation. Thank you so much for listening, and I will be glad to answer any questions. If you have any questions, please feel free to ask.